Pharmapal.
Cross-docking of inhibitors into CDK2 structures. Welcome back to our channel. Today, we're diving into an exciting study on protein-ligand interactions, specifically focusing on the cross-docking of inhibitors into CDK2 structures. This research sheds light on how we can improve the accuracy of docking protocols, which are essential in drug design. Let's break it down. First, let's understand what CDK2 is. CDK2, or cyclin-dependent kinase 2, is a crucial enzyme that regulates various cellular processes through phosphorylation. Inhibiting CDK2 can be a potential strategy for cancer therapy. Now, docking methods are computational techniques used to predict how small molecules, like drugs, bind to a target protein. However, accurately predicting binding affinities has always been a challenge due to the flexibility of proteins. The researchers aim to answer several key questions. Does docking accuracy improve when analyzing multiple related complexes? Can we predict relative binding affinities from docking scores? What are the pros and cons of cross-docking in modeling protocols? Can we replicate the effects of protein flexibility in docking? These questions are vital for enhancing lead optimization in drug discovery. To tackle these questions, the study utilized 150 high-resolution crystal structures of CDK2. Here's a quick overview of the methodology. Protein preparation. The researchers aligned the structures to a reference CDK2/ATP complex and ensured all ligands were correctly protonated. 3D structural diversity. They calculated the ATP site volume and RMSD values for key active site residues to assess structural diversity. Cross-docking. Each ligand was docked into all 150 structures using two docking programs, GOLD and GLIDE. This allowed for a comprehensive analysis of docking accuracy and scoring performance. The results were then analyzed to determine how well these methods performed in predicting binding affinities. So, what did they find? Docking accuracy. Both GOLD and GLIDE showed promising results, with a 50% chance of docking a ligand within 2A of its experimental pose. Scoring functions. However, the study revealed that predicting binding potency from docking scores remains challenging. GLIDE performed slightly better than GOLD in this aspect, but both methods had limitations, asterisk. In fact, the correlation between docking scores and experimental binding affinities was not as strong as hoped. This indicates that while docking can guide the selection of potential drug candidates, it should not be solely relied upon for predicting binding strength. Next, we'll break down the figures presented in this paper, making complex concepts easy to understand. Let's get started. First up, we have Figure 1, which illustrates the docking frequency spectrum for both the GLIDE and GOLD docking methods. The graph shows how often ligands were successfully docked to the CDK2 structures. Notice that for GLIDE, the docking frequency is represented as negative values for simplicity. This figure highlights the effectiveness of both methods in predicting ligand binding positions. Key takeaway: GLIDE and GOLD perform well, but GLIDE shows slightly better docking frequency. Moving on to Figure 2, this figure presents the 3D structural diversity of 150 protein structures. It highlights the ATP site volume and how the key active site residues, like TIR15, VAL18, LIS33, Phe80, and ASP145, vary in their positions compared to a reference structure. What to note: the ATP site cavity volume ranges from 350 to 660 A superscript 3, with most structures around 550 A superscript 3. This variability indicates the flexibility of the active site, which is crucial for understanding how ligands interact with CDK2 asterisk. Figure 5-8, RMSD distribution. Next, let's discuss figures 5 to 8. These figures showcase the centered histograms of RMSD values, which measure the differences between the docked poses and the actual crystal structures. The histograms reveal how many compounds were docked within a certain RMSD threshold. Insights. Figure 5 focuses on a cutoff of 1A, while Figure 6 examines a 2A cutoff. The data indicates that relaxing the RMSD cutoff significantly increases the number of compounds that can be docked accurately asterisk. Figure 9. Correlation of docking scores with binding affinity. Now, let's take a closer look at Figure 9, which is crucial for understanding the relationship between docking scores and binding affinity, represented by log IC50 values. This figure is divided into several parts, each showing different correlations based on the RMSD cutoffs. Panel A, ideal correlations for glide and gold scores with log IC50. Panels BD, these panels illustrate the correlation distributions at various RMSD cutoffs. Key observations. Glide tends to show a stronger correlation with binding affinity compared to gold, especially at lower RMSD cutoffs. However, the overall ability of both scoring functions to predict binding affinity remains limited, emphasizing the ongoing challenges in computational docking. In conclusion, this study highlights the importance of using multiple protein structures in docking protocols to account for flexibility. The findings suggest that while current docking methods are useful, there's still room for improvement in predicting binding affinities. As researchers continue to refine these techniques, the potential for discovering effective new drugs increases. Thanks for tuning in. If you found this video informative, please give it a thumbs up and subscribe for more insights into the world of drug discovery and computational chemistry. Have any questions or topics you'd like us to cover next? Drop them in the comments below. Until next time, keep exploring the fascinating world of science.
Pharmapal.